Hello everyone and welcome to Tech Talk session number 25, Paul Stechik with NEPSI. So today the presentation is going to be about NEPSI's and AMSC's solutions for renewable power plants. This week we're going to focus more on what NEPSI has been doing, and we're going to just touch a little bit upon what American Superconductor brings to the party, AMSC's DVAR and STATCOM product line and VVO product line. And next week we're going to have them online to talk more in detail as to what their systems can do. So the NEPSI solutions for renewable power plants, we're going to be talking about cost-saving opportunities, how our products can save the developers on cost, and what you should be doing as a developer, what you should be specifying and telling your engineering firms, your EPCs, what you want in your systems. So we're going to get on with the presentation. Alex, maybe you can pop me down and we can get the presentation going. So let me just get on with the presentation here. All right, let me see. Well, there we go. All right, so it's just a couple housekeeping things first. Don't forget PDH contact hours. If you want to get some certificate at the end of the presentation, just give us the code and we'll get a certificate off to you. And also, don't forget what NEPSI does. We manufacture metal closed capacitor banks and harmonic filter banks. And now being part of American Superconductor, we're also integrating their STATCOMs, their DVAR and their VVO products into our product, and we can offer their products as part of our solutions. And we'll be touching upon that just a bit today, and then again next week, more in detail on that regard. So just key products that we're going to be talking about today are shunt power capacitor banks and harmonic filter banks, shunt reactor banks, and more or less when we do shunt reactor banks, we're providing inductive VARs. It means we're taking VARs from the system, more or less dropping the voltage is what we're doing. And then we have hybrid shunt capacitor and shunt reactor banks. So that is what today's Tech Talk is about, are those products. Remember, NEPSI is a metal closed equipment supplier, which means that all of our systems come fully integrated with all switching, all protection, and all control. These are products that supply reactive power or consume reactive power. It's for voltage support oftentimes, and it's oftentimes there for grid code compliance. So if you're a renewable power plant, you're interconnecting onto a larger electrical grid, you need to have grid code compliance. And there are typically interconnect studies that are conducted, and those interconnect studies are conducted by engineering firms. They dictate the amount of reactive power you need to meet certain criteria within the system. Incidentally, NEPSI can be involved with the harmonic analysis and with filter design and the power factor study portion of it. And now that we're part of AMSC, we can also have support with their planning group for the study support for grid interconnect studies. So we are basically providing almost a full turnkey of options for the renewables industry. So today's presentation, we're just talking about solar and wind. And don't forget, we sell into all the different industries: solar, wind, petrochemical, utility, mining. When you think about metal closed systems, cap banks, filter banks, remember that the flavor of a capacitor bank or harmonic filter bank is going to change based upon the industry. So today we're talking about solar and wind, which is really dominated by 38 kV equipment, 34.5 kV equipment, and not typically 2.4 kV up through 25 kV. Typically it's almost always at 38 kV. Also remember that NEPSI builds metal closed solutions on the left, which is a fully integrated solution. It comes with all switching, protection, and control, and it's tested at our factory before it leaves our factory. The stuff on the right here, we do not build. It's open air solutions. And really, we're talking about the cost advantages of the metal closed solution when compared to this open air option. And here you can see this is a capacitor bank here on the right, and it takes up quite a bit of footprint here. We're going to be talking about all these advantages and cost saving opportunities by going from a open air solution to a metal closed solution. So we're going to be talking about those details today. Just as a quick summary of, and here's an example of a fully integrated solution that we recently supplied into a wind farm. Just look at the stats here. It's a 12 MVAR 4.7 tuned harmonic C high pass filter. That filter was put in place for resonance dampening. We've talked about this before. Whenever you install a capacitor bank on a system, you are causing resonant conditions. When you have a wind farm with a lot of cable capacitance, you have resonance concerns. These turbines over here oftentimes are very good from a voltage and current distortion point of view, but typically they're putting out low levels of harmonic current distortion. Even low levels of harmonic current distortion, when injected into a resonant condition, can cause problems. So oftentimes wind farms, solar plants are plagued with this problem that they might have a resonance issue. So you can answer that problem up front by putting a C high pass filter in. I got it right there. This is also a 3-stage capacitor bank. So you get 12 bar filter plus a 3-stage capacitor bank. Remember, the 12 bar filter provides reactive compensation, provides filtering, and it also prevents resonance. The 3 reasons why you might want to install a filter on a system. The capacitor banks are there to supply reactive power also. So a total of 48 megabars here. And then during light load conditions, we had to put in this 5 bar shunt reactor bank. So basically we had a 5 bar shunt reactor bank because we were looking to have that 12 bar system on at all times. So this picture here represents that piece of equipment, and this is what NEPSI does. So I want to show you a 3-line diagram of that system. It's quite involved. We had a incoming area here, PTs and CTs on the incoming lighting arresters. We've had disconnect switches inside our equipment to provide isolation to allow for maintenance of the equipment inside. We can basically get into a portion of the equipment here, while the other portion, say over here, is in fact energized. You can see here on the left that stage 1 was a 12 bar C high pass filter, and then we had multiple branches of capacitor banks here that were filter ready. Okay, so they're harmonic filter ready. We're going to talk about this concept of filter ready further on in the presentation. It's important to always remember that when installing cap banks on any system, but especially even renewable systems, that there is that possibility of resonance. And what you'll find if you talk to any studies engineer who's conducted harmonic studies on these wind farms and solar plants, is you'll find that the solution or the results of the study are oftentimes inconclusive. You might have a harmonics problem, you might not. And this is a big issue with the harmonic studies that are conducted for these industries. And it takes a little bit of maybe doing that study work to understand why this is the issue. But you have caps, you have the collector system, they cause resonance, you have low-level harmonics. And the question is, you do not really know exactly the system, so you cannot always exactly predict whether or not you have a resonance issue. And the other thing is that IEEE 519, the 2014 standard, is quite strict when it comes to renewable power plants. You're squished down to the first row in the distortion limits at the point of common coupling, so therefore it makes it difficult to meet the standard. So this is a fully integrated solution. It has a lot of advantages. Just looking at it on the surface here, you can kind of see it's a very complex solution, but it's in a very small footprint. This is a very small enclosure system. If this was an open rack system, you would have air core reactors for both the filter and the shunt reactor stage. You would have elevated structures for all the capacitors, and it would take up a football field. Realistically, it would take up a football field. It would require a lot of site work. It would require a larger foundation area here, so a larger ground pad, more rock and stone, more fence over here, okay, more lightning protection, more site work, and therefore this metal closed solution, when you consider all cost, the metal closed solution will come out to be less. And we're going to show some slides that talk about costs later in the presentation. So just moving on, these are the impedance scans, and this is the kinds of studies that NEPSI will get involved. We'll develop the impedance scans, and here you can just see the classic impedance scan. We have the system here in the green before we put any capacitor stages on. We have a resonant condition. The collector system, along with any filter that might exist inside the wind turbine, will create some type of resonant condition in the system. This, of course, becomes a concern for the condition where we have nothing online. As we kick stages on, you can see here our resonant point moves around. And here you can see we're kind of over the 5th harmonic. Here we're close to the 7th. And even with some shifts in the short circuit impedance, the grid strength, as we noted here, we're going to have these possibility resonances. And these are concerns that the developer will run into. Well, one solution to that is to put a C high pass filter in, and that's what we did with this customer. We added this C high pass harmonic filter branch at stage 1. And what we did, and it's kind of interesting to note here, is you can look at the axes of the curve here. This is the impedance curve, and we have Z per unit here. You can see that the peak, the worst resonant condition, peaks out at about 35 per unit. If I kind of go back to the previous slide, you can see that here we have 700 per unit. So what this means is that what we're looking at these curves, remember, I think we've talked about in other tech talks, is that if we have harmonic current injection at these various harmonics, is the current times that impedance gives you the per unit voltage. Okay, so here you can see that there's a magnification concept here because of resonance. Putting that C high pass filter in, we eliminated, basically dropped that per unit impedance to a maximum of 35. Okay, so it's a very interesting thing here. One C high pass filter, 3 capacitor stages, and we reduced the magnitude of the worst case resonant condition to 35 per unit for the impedance. And that's an interesting concept. So this is another project where we did, and here it was a 2-stage cat bank, filter ready. You can see the filter ready concept here, and we're going to be talking more about this. These are removable panels in the back for passing through into a reactor cabinet, which would also contain a potential for aux capacitors and resistors to create filters. But if the system is filter ready and you were to start the system up and to have a problem, say you have a resonance issue, we could quickly put another pad on the back here and create a harmonic filter system. And in this case, the customer would not be stuck with a capacitor bank that does not function or does not work. So that's the advantage of this system. So this is a 2-stage 15.7 and 15.7 M-bar for capacitors, and it's got this shunt reactor 4.1, and we're going to be talking about that, and that's here. It's a shunt reactor, and it's an iron core reactor immersed in oil, so it's very compact. Again, a very compact solution for this customer. And we have outrush reactors here. We have a tech talk where we talk about the requirement for outrush reactors. Maybe 3 or 4 tech talks ago, we talked about that requirement for outrush reactors. Here's that. Here's the one-line diagram for this system. So, interesting thing to note here is that the switching device oftentimes plays into the cost of the equipment and also the delivery time of the equipment. So we're going to talk about that too in a moment. Over here we have a shunt reactor bank, and you can see here we put in RC snubber. So shunt reactor switching is a very difficult process. We like to use SF breaker, and we put in an RC snubber here to reduce any possibility of reignition within the breaker itself. The capacitor stages here, we're going to be talking about these switching devices here. And again, capacitor switching at the medium voltage level 38 kV is also something that can be difficult for the switching devices. So we're going to be talking about what choices we have in the switching devices here, because that overall determines the cost of the equipment and also the footprint of the equipment and the lead time of the equipment. So we're going to talk about the metal closed solution, how it gives you choice. When you're in an open air solution, you really do not have a lot of choice of your switching solution. So let's just summarize here. Since we're in the renewables area, we're sitting at that 38 kV level. So 34.5 kV is the nominal, multiplied by 1.1, and you got about 38 kV. System voltage frequency, 50 or 60 hertz, no issue there. The reactive power rating of the equipment is really limited by the switching device. Okay, so when you talk about metal closed solution, our limit is based upon the switching device. I think we've gone up to about, I think maybe 18 MVAR per stage. We've done systems as large as 75 megavars in a single lineup in the past. It's very typical that we might have 4 stages of 12, like we had showed you earlier, or 4 stages of 15 megavars. So they can get quite large, these systems. So remember, reactive power rating is really dependent upon the switching device, and we'll talk about that in a moment. The installation rating. when we're talking about insulation rating, we oftentimes see the metal enclosed solution being specified at 200 kV BIL, or we see that the open air system is specified at 200 kV BIL. The point here to be made is that we prefer 150 kV BIL. And if you were to go to the standard, you would see that, let me see here, if you go to the standard, you would see that we follow the C37.20.3. You will see that here, for a 38 kV gear, the requirement is 80 kV withstand, which means basically we're going to put 80 kV across the terminals of the equipment to ground, and we're going to test for 1 minute. So it's 80 kV withstand. It's a 1 minute withstand, and the impulse rating is 150. You do not need to have 200 kV BIL. So it's very common that for open air solutions, 200 kV BIL gets specified, but for metal enclosed solutions, specify 150. And there's reasons you want to do that, and the key reason you want to do that is that if you go to 200, it will squeeze the number of switching devices that can be used. Basically, you're going to push us into one switching device. If we keep it at 150, we're allowed to use breakers. Okay, we can use the ABB VD4, the ABB VD4CS, and the HD4 breakers. Those carry a less cost than the alternate switching device that we'll talk about in a moment. And oftentimes the lead time is much less. In fact, we stock the VD4 and VD4CS here at NEPSI. So by going with 150 kV BIL, you're allowing us to have choice in what we choose, and it also allows us to give you some cost savings. So 80 kV withstand, again, is what we prefer here. So the other item to think about is short circuit rating. We oftentimes see the engineering firms automatically specifying 40 Ka, and a lot of times we can do the calculations and we see that 31.5 Ka symmetrical fault current works for you. So I'm going to talk about why this is important too. This is a comparison of switching options, and when you think about what switching devices are available to you as a capacitor bank, as a customer to purchasing capacitor banks, you have a choice of breakers, and we list them here, the VD4CS and VD4 and HD4. But you would also have the Southern States cap switcher, which, by the way, is an outdoor solution. So if you go with the 150 kV BIL and 31.5 Ka, it allows us to squeeze into using these other breakers. Okay, so Southern States cap switcher is a switch, it's not a breaker. The VD4CS is a vacuum breaker with synchronous closing technology. It uses servo motors. We have a whole video about this technology on our website. The VD4 is a standard C2 rated breaker. When I say C2 rated breaker, what I'm talking about is a breaker designed for capacitor switching. It means it has a very low probability of restrike. HD4 is an SF6 breaker, and we would typically use this for switching shunt reactor banks. And you want to use SF6 when switching shunt reactors. And then finally we have the RL switcher, which is a very large switch from Southern States. So these are I would call the major choices that you have when you are choosing which switching device to use. And these are the choices that we have and the ones that we most often use. So the Southern States cap switcher is an outdoor rated device, and the Southern States RL switcher is also an outdoor rated device. The breakers are indoor. So if you specify outdoor rated equipment, you are forced to use that technology. One of the key advantages to the open air solution is that we can use a breaker because we're putting the breaker inside the enclosure. We can use a breaker, and there's a lot of cost advantages associated with that, and that's really one of the things to think about. There's some cost advantages, and we're going to talk about that in a moment. Let me get back to where I was. So short circuit rate, if you specify 31.5 Ka, we can use those breakers. and we can use the switching devices. And what it really is going to do is it's going to help you eliminate the feeder breaker in front of the cap bank. And we're going to actually show a one-line diagram of a typical collector system to show you how that breaker inside our equipment can serve as a purpose for both switching and short circuit protection, and we can eliminate an upstream feeder breaker. So a key thing to think about. We could put an integrated isolation switch in our equipment too. We have an ABB 38 kV Versaruptor that we can put into our equipment. And basically what that does is it's going to eliminate the upstream disconnect that you might have in the substation. So we're going to show also how that can save on cost. But basically what we're doing is we're putting more into our package and you're putting less into the main substation. So it's more of an integrated solution and reducing costs, reducing site costs, installation costs, purchasing costs, and so on. So capacitor switching, we talked about that already, the choices you have between the breakers, and we're going to show some pictures of that. The control and protection is something else that's interesting. For most projects we see that the customer, well, the developer or the engineering firm involved with the equipment will put the control and protection system into the e-house. So they got the rack on the outside, or the capacitor bank, even the metal closed cap bank is inside the switchgear yard, but all the protection and control relays get brought into the e-house. And you can see here on the left, this customer had chosen to put all of the protection and control into our cabinet. And what that does is it eliminates all the costs associated with running the A and B contacts, the trip and close contacts, all the indicators, all this this wiring that would exist between the main capacitor bank and the switching devices and the current transformers and so forth are brought back into the e-house, and there's a significant amount of site costs associated with that. Well, if you specify that the control and protection system is part of the metal enclosed system, it means that we're installing all those relays into our equipment. We're testing before it leaves our factory. We're setting them before it leaves our factory. It means that it shows up to your site ready to go. Here you can kind of see a trunk of cable, and I always like to kind of point this out. If that trunk wasn't going into our cabinet, it would instead be going to the e-house, and that means that you'd be running troughs to various components within the substation to make those connections, and somebody would have to bug those out. So just think about the time savings that you have when you put the control and protection system into our equipment. So anyways, so we're going to move away from this slide and talk about some cost saving opportunities. And sorry about that. One is an integrated solution. It offers low risk. We're taking on the entire project. We're doing it basically turnkey. We're not doing the install, but we're handling all the design, engineering. We're setting the relays. So it's a fully integrated solution. You order one piece of equipment. That's it. It's that simple. You can get a integrated shunt reactor with the equipment. That means that you're not going out to a reactor supplier and installing that equipment there, and you're not deciding what switching device to use, and we're taking care of all that. The reactor we're using is an iron core oil immersed reactor. It's got a very small footprint. It's very compact. Because it's integrated into our gear, it means it's using the same disconnecting device within our gear. We're installing a breaker in our gear with an RC snubber, and that's a very cost competitive solution when compared to, say, an outdoor RL switcher. So you can have some cost savings there. When we're going metal enclosed, we got the choice of alternate switching devices for both the capacitor bank and the reactor bank. The equipment can be supplied with roof bushings, so you can park the entire enclosure underneath the bus bar structure, or we can give you a cable entry. You can come in with cables. So it allows you to have flexibility. Where do you want to put the metal closed cap bank or filter bank within your substation environment? We offer a reinforced floor system in our metal closed systems to allow for mounting of the metal closed system on pylons. Okay, so sometimes depending upon soil conditions, our customers will put our equipment on pylons, easier to drive pylons and get the support you need on pylons rather than pouring a concrete pad. NEPSI can be involved with the harmonic analysis. We could tell you what the possibility of resonance is, if you should be buying harmonic filters, and we can oftentimes do this at a very competitive price, and oftentimes we will include it with the metal closed cap bank if you purchase from us. And then we always, of course, recommend filter-ready cap banks because harmonic studies are often very inconclusive. So we recommend that you buy a filter-ready cap bank and do a wait-and-see mentality. I think we have a tech note, a tech talk earlier this year, maybe Tech Talk 10 or 15 in that range, where we talked about this filter-ready concept. So it's a very important concept to think about and to specify. So here we're looking at, well, let's do a price analysis. And this price analysis was conducted, by the way, by an EPC. And this was the numbers that they came up with, not the numbers that we came up with. So this company was in the process of trying to evaluate, should they go with open air or should they go with metal closed? And they factored in all the costs associated with the 2 9 megavar cap banks as an open air solution, and they came up with a total installed cost of $312,000. So it includes the equipment and component cost as well as the site and commissioning costs, so $312,000. When you compare that to the metal closed option, this same EPC came up with a total installed cost of $291,000. So a lower cost, a cost savings, and a lot more simplicity. And that's really the key here, more simplicity. You had saved, I think it was $291 versus 312. All right, so $20,000 or so. So a decent cost savings and a lot more simplicity in the choice. You can see what's going on here. The site and commissioning costs are squished down to the small area, but the equipment cost is more. So, of course, you're purchasing a completely integrated solution. It's coming to your site. You're lifting it off the truck, you're putting cables to it, and you're basically done. So the cost is incurred in the purchasing of the equipment, where on an open air solution, you can kind of see that the cost of the install and commissioning is a lot more, but the component cost is less. And what we have found is that more and more the metal closed option is becoming a preferred option because it's being understood that when you factor all costs in, the metal closed solution is less expensive. So let's just talk about your switching options. Remember, if you're open air, you're going to be pushed into this category here because the Southern States cap switcher is an outdoor rated device. Open air meaning everything's exposed to the environment, and you're forced into that technology. You're forced into their lead time, and one thing about the Southern States cap switcher you have to realize is you do want to plan ahead because there is pre-insertion resistor technology here. The rating of this resistor is based upon the table, and you have to wait until the study is completed to choose the resistor, and then you have the proper switch. This is more or less a de facto standard when it comes to the outdoor switching devices for capacitor banks. Everybody knows who they are, and I would say one of the drawbacks is lead time. Historically, it's been long, and what makes things worse is a lot of times the grid interconnect study is done late in the game, and if you have to wait till late in the game to order the switch because you don't know the size of the cap bank, it can also be one of the critical items to plant completion. So going with other switching technology, not only is there some cost advantages and lead time advantages, you can get those items on order up front because there is no resistor sizing there. So for smaller banks, we would typically use just a standard VD4, which has a very price competitive, is very price competitive. For larger banks, we would use this VD4CS, which is a new breaker out by ABB. We have 2 videos here on in our playlist. If you go to our website, you can learn about that switching technology. We actually do a comparison to the Southern States cap switcher to learn about that switching device. But one of the key advantages of using a breaker is this 31.5 kA rating to it, is that we can eliminate the feeder breaker upstream. And then we have the RL switcher, which is another outdoor device that we would typically use for reactor switching. And the alternate switching device for that would be the HD4 here, which is an SF6 rated breaker. All right. So if you guys want a copy of this comparison of the switching solutions, just contact me. This is a table which compares all of the switching solutions that you basically have in North America, the ones that we're dealing with, and you can do a comparison of those ratings. There's a lot of information here. Can't go through it all today, and the tables continue. Just some pictures here. On the left is a Southern States cap switcher. It's exposed to the environment, and on the right you got a shunt, a RL switcher with the air core reactors. So air core reactors in the background here, the RL switcher in the front, and this is how the outdoor structures look. On the inside, the enclosure, we can park a Southern States cap switcher in there. We do it very often. There is some people in the industry prefer that Southern States cap switcher. We can put that inside our gear. It works very well. This is the RL switcher in our gear here. You can see one of the major issues here is it's very tall. So we have to do a bump up in the enclosure, and that becomes a difficult thing. We can also use the breakers, and this is really something to plan on, is that there are some advantages of using the VD4 and the VD4CS from a cost standpoint and from a lead time standpoint, and then also from an advantage standpoint because we can eliminate that upstream feeder breaker. So incidentally, what you're looking at here is a VD4 breaker, and we got transient inrush reactors here. If it were a VD4CS, one that was doing synchronous closing, it would not have those reactors. It would, because we're doing synchronous closing, no reactor. For shunt reactors, we have air core on the left, iron core on the right. Most oftentimes we're doing iron core reactors, but there is a cost break point where iron core reactors become more expensive than air core reactors. I kind of skip ahead to it here. And really that the component cost the breaking point is about 4 to 5 megavars. Remember, as you're think about this, if your megavar goes up, your X-eval, the inductance value, goes down. Okay, you have less turns. So there's a crossover point where the iron core reactor is just plainly more expensive from a component cost standpoint. There is an installation component to this too, and I put that shaded area in red. That crossover point actually will be pushed to the right a little bit if you start to think about the cost to install those air core reactors, because they can get quite large. If you're in a high seismic zone area, you have to then consider the footings and the cost of the footings and the elevating structure. They can also get very expensive. The iron core reactors are sitting at the ground level, and you don't have as much of a difficult time dealing with the seismic related issues when you're dealing with those high seismic zones. So iron core reactors is something to think about, and we're just going to kind of flip through social pictures real quick. These are the typical drawings, and the reactive power rating typically is about 0.25 MVAR up through about 20 MVA, 20 MVAR. So we'll include all the switching, protection, and control when these reactors are equipped on the side of our unit. Basically, we have to ship these things separate. Here you can see we have a plate that we've installed, and we remove that plate, slide the reactor up against it, and the connections are made. So it's a very simple process to install an iron core reactor within the gear. This is the RL switcher, which would be used to switch a shunt reactor if we were to go in the direction of using an RL switcher instead of a HD4 breaker. All right, so this is a drawing, and I should probably give credit. This is an NEI drawing. NEI is located in Denver, Colorado. They do a lot of renewable projects. So I'll note that I did take this drawing from a package that we were asked to bid on a while back. And so do be aware that that's where this drawing came from. Certainly reach out to them if you are in the market for doing some type of design for your project. So the shaded area represents the reactive compensation for this project. So on this project, there was 2 capacitor banks located here. These are the switching devices. So you got cap bank here. You see here there's a neutral CT or a neutral PT, cap bank, switching device. Again, that switching device could be a Southern States cap switcher, or it could be a VD4 or VD4CS. And then up here, there's a breaker. This is a feeder breaker here. So this feeder breaker has to be installed because if there's a fault down here within the capacitor bank, you got to have short circuit protection. And then you have a gang operated switch here. So gang operated switch, feeder breaker, supplying 2 capacitor bank stages and 1 shunt reactor stage. So that's the design requirement for this project. And there are some cost-saving opportunities here. This is an open-air design. So this was a project that we were asked to bid as an alternate to an open-air design. The first thing I'd like to note is we could eliminate this disconnect up here and put that disconnect into our enclosure. We could also eliminate this breaker if we were to eliminate the cap switchers here and install VD4 CSs or VD4 breakers instead. So if we put the short circuit protection down here inside these here as breakers, we can eliminate this breaker up here. So that could be anywhere between, say, I don't know, say 30,000 costs or 50,000 installed costs in the project. Plus you got your actual gang operated switch there. And then over here to the right, you got the shunt reactor bank. And again, if we make that a breaker, okay, we're eliminating this breaker here. And the RL switcher, incidentally, has a higher cost than a comparable HD4 breaker that we would put inside our enclosure. So there are a lot of cost-saving opportunities here. And if we were to look at it from a layout standpoint, the area in red here represents that shunt reactive system. So remember, shunt reactor, bank plus capacitors. And NEI did a really good job here because they did make this a filter-ready system. You can kind of see here on the left, we got shunt reactors. There's the switching device, some stands for bus bars. We got bus bars here, switching device, and there's a space here for reactors. So the question is, okay, I'm going to install a cap bank now, but in the future I might need a filter bank, and NEI left space there for tuning reactors. And then up on top here, you got the capacitor rack itself. So this is the layout. Here is looks like a doghouse breaker. It could be like an RMAG breaker here, and then a disconnecting device. Okay, so we're calling all of this shunt reactive system for this project, and that's the layout. We could instead take a metal closed solution, and this is a 3-line diagram of a metal closed solution, and replace that open air system. And what's interesting here, you can kind of see we've taken all of that area and we've pushed it down to just this small area here. And this is a filter ready cap bank with a shunt reactor on it. So kind of this is how it looks. So it's much simpler. It's a single enclosure with a shunt reactor on the end. This enclosure here is a add-on piece should in the future that cap bank need to be converted to harmonic filter. So just a side view here, shunt reactor on the end. The 2 capacitor stages here, you can kind of see the ground switches with windows, and we have roof bushings coming in, going to the overhead gang operated switch. And again, we show this gang operated switch. We could push that gang operated switch down into the enclosure here and eliminate that also. So another savings and cost savings opportunity. And we decided we would, when doing these drawings, to also show, well, how does it look if we use air core reactors? So remember, we have a crossover point for shunt reactors. If you get above that, say 5 MVAR range, maybe air core reactors is a avenue you want to explore. So in this case, we did a set of drawings and we put roof bushings on the exit to exit out and go to a shunt reactor bank that is air core reactors. So if you're trying to keep the project as competitive as possible, you could go to Trench or Phoenix, buy the air core reactors separately. We'll still put the switching device inside our enclosure, but put roof bushings in, and then then you can purchase their air core reactors by themselves. So as you get up into that 10 or 20 megavar range, maybe the iron core reactor is not competitive from a price standpoint. If you want to keep the project as competitive as possible, then go with these air core reactors. You can see here the size of these air core reactors. They're really large in size. And there's 3 reactors, 2 in the front and 1 in the back, kind of in a triangular format. One of these things about air core reactors is you got the magnetic field that you need to be concerned about. So you need to have spacing between where the reactors are and all metal parts that form closed loops. And that spacing factor is typically 1 times the diameter of the reactor away from the reactor area. So it can be quite a large area that you're dealing with. Here I just want to talk about filter-ready cap banks for a moment. Remember, whenever you install a capacitor bank, you have resonant conditions, and because you have resonant conditions, you might need to install filters in the future. So whenever you install a cap bank in the renewables area, because the studies are not conclusive, NEPSI has a recommendation that you always install filter-ready cap banks. This area in yellow is what it takes to convert a standard cap bank here to a harmonic filter. So if you purchase a cap bank, if you specify filter-ready, what it means is that you're going to specify higher rated capacitors, and you're going to specify the provision for it to be converted to a harmonic filter. That conversion process involves the installation of a reactor bank, a cap bank, and a resistor bank. So, and that's what we talk about here. You're going to buy HD or EXD capacitors if it's an Eaton capacitor. Typically 34.5 kV, the line to neutral voltage is 19.9. So maybe you would go with a 21 kV cap or a 22 kV cap, which means you have to buy more kVAR up front, but the cost per kVAR, when you're just talking about kVAR, is very inexpensive. So it's pennies on a dollar at this point to install that higher rated capacitor that you would need if it were to get converted to a harmonic filter. Provide the provisions for that, and this is whether it's open air or metal closed, you should be thinking about filter ready all the time. We oftentimes get phone calls that said, hey, I got a resonance issue, I just purchased this cap bank, can I convert it to a harmonic filter? We ask a few questions and we find out that they didn't have space in the substation for the reactors or the resistors. The capacitors don't have the voltage rating they need, and the customer, the renewables developer, is out of luck. They're out of luck because they purchased something and they can't use it. So making sure that you specify that cap bank up front correctly is really important. And the filter ready bank should include drawings for the future. All right, so if you have a filter-ready cap bank, make sure that the drawing package that you're approving in the end includes the provisions. How will it look when you convert this cap bank to a filter? Make sure that the substation layout drawings include the future filter bank. You got to have space in there. If I have to convert this to a filter, I need space in that substation. Make sure it has a space. So this is pretty much standard for what NEPSI does for the metal closed solution. We will show that space requirement in the substation to convert a cap bank to a harmonic filter bank. The other thing that we would recommend is that you install a Schweitzer 735 on the capacitor bank, and then also on the mains to the plant itself. So you got the main incomer, put a 735 there, a power quality meter from Schweitzer, and then also put one on a cap bank. If after startup you have problems, you do not need to send somebody out to site to take harmonic measurements. You can pull the device itself and obtain the necessary harmonic data for us to do a filter design. So we recommend that because, again, the cost savings are significant if you do have a problem. This is a 3-line drawing representation of a filter-ready cap bank. Again, the shaded area in yellow you would not get up front is something that we could add on at a later date. The enclosure itself has pass-through areas in the back that allow for the passing of medium voltage from a capacitor bank section into a reactor / aux capacitor / resistor compartment. It would have all those. And that's what you see here, in the provisions here. The shaded yellow area represents what it takes to convert a cap bank to a harmonic filter bank. You need a resistor cage on top, potentially, and then a reactor and potentially an aux capacitor stage down below. And we would just pass bushings back and forth here. So in the end, you have a pad requirement or a spacing requirement within the substation that includes the standard cap bank plus basically a double depth of that cap bank to include this yellow area. And that would be the requirement within the substation. So it's not a significant cost increase in the equipment because everything is an add-on. You're not adding a lot of cost to the substation because it's just a very small area and you've got yourself covered. We can convert those cap banks to notch filters. We got other tech talks that talk about filters and types of filters, but we can convert that to a notch filter, a high-pass filter, and a C high-pass filter. Most oftentimes when you do have a resonance issue within a renewables plant, we're pushing to a C high-pass filter. And like we did at the initial slides in the beginning of this presentation, you can get a very significant damping factor within the filter, and we can eliminate resonance concerns associated with capacitor banks and even the collector system cables. So, and really here we're just showing slides. I've done this before. The difference between notch filters and high-pass filters is the elimination of the resonant points that you get here between notch filters and damped filters. So C high-pass filters and high-pass filters eliminate the resonant points that exist below the tuning point of a notch filter. So in conclusion, if you're a renewables developer, and this is key, if you're a renewables developer, if you want all the advantages, the cost savings associated with metal enclosed cap banks, you have to specify it. The engineering firms are going to cut and paste what they've been doing, and this is a fact. We've been seeing it for years. There's a desire to push out the drawings fast. If that engineering firm doing the work is used to doing open air solutions, they're going to cut and paste the previous open air solution into your drawing set. So you have to say, no, I want a metal closed solution. I want the metal closed solution. I want the advantages associated with that. Otherwise, you, the developer, will most likely get an open air solution unless you're working with one of those engineering firms that has already started working with this metal closed solution concept. And I can tell you more and more engineering firms are working with metal closed solutions. More and more developers are specifying metal closed. We see that because we see a rectangle in a substation. And if you think about it from an engineering standpoint, the engineering firms that are still doing open air solutions, the metal closed solution is by far easier to draw. Take a rectangle, put it on the drawing, and you're done. If the size of the bank increases in rating, make the rectangle a little bit longer. It's very easy. I can't stress how easy it is. Inside that rectangle will be everything, but from your drawing standpoint, that's all you need. So a specified metal closed, it's only a rectangle in the substation from your standpoint. We have a standardized drawing set, basically saying if I need a 2-stage, a 3-stage, a 4-stage, how many megavars you need, you can get a budgetary length for the size of that rectangle. So send us an email, ask for that template of coming up with the size of the rectangle, and we will give that to you. When we specify filter ready, okay, it's going to come at almost no cost, and it's backup insurance for the developer. If you got a resonance issue, Filter Ready is going to take care of you. If you have a utility that's putting on a meter at the point of common coupling, there's a very, very good chance you could potentially fail IEEE 519 at the point of common coupling, especially at high frequencies or at one frequency. So having a backup plan is very important. Specify 150 kV BIO, not 200. And if you do that, it allows us to use more components within our gear. It gives us more choice, and we can pass cost savings on to you. It is well within the IEEE standards to use 150 kV BIO. We're not exposed to the environment. We don't have concerns that the open air guys have, which is contamination of the insulators or bird strike against the insulators themselves and flashover. Because we're inside the enclosure, we're protected from the environment. We don't have to worry about rodents in the 150 kV BIO. It makes sense at that point. So 150 kV BIO is preferred. If we need to go up, cap it at 185. 185 will allow us to use the VD4, VD4CS technology. We will just have to eliminate the disconnect switch. The disconnect switch that we use is 150 kV BIO. So don't overspecify the short circuit rating. Calculate the short circuit rating. If it's 31.5 kA or less, specify at 31.5 kA. They'll go straight to 40. And in so doing, we can use the VD4CS and the VD4, both of those switching devices, which are designed for capacitor switching. There will be a cost savings to you and a definite lead time savings to you. The lead time could be down as short as 8 weeks for the entire project. So the metal closed solutions can ship, say, I'm going to shoot this out there, as little as 8 weeks if you really need the equipment. But typically we're down in that, say, 14 to 15 week time period. And consider the cost savings. When you're evaluating our equipment, consider the cost savings. Remove the gang operated disconnect switch in front of the equipment. Remove the feeder breaker in front. Because we have breakers in our gear, you're going to pass that collector bus basically into our gear, and you're just adding 2 more additional breakers or 3 breakers, whatever number of stages you have, and those breakers will provide the short circuit protection, so you have a savings there. And then think about incorporating the control and protection system into our system. If you do that, it eliminates all of the site work and all the testing on site, because it's going to leave our factory in 1 or 2 pieces and it'll be ready to go. So the Tech Talk today, 432 for the contact hours. And I will look for questions in a moment. Next week, we're going to go with this hybrid STATCOM systems. You want to shrink me for a second so everybody can see it. This is really the synergy between NEPSI and AMSC. There's a lot of synergy. AMSC has been in this STATCOM business since the 90s, early 90s. We've been in the metal closed passive solutions since the 90s. With the acquisition of NEPSI by AMSC, we can now offer a fully integrated solution. And with us next week will be AMSC and their product engineers to talk about the hybrid STATCOM systems, hybrid STATCOM filter/cap bank systems. And this is really a way to really get additional cost savings by utilizing an integrated solution that includes a STATCOM system over here and also the capacitor bank itself. We can install fast discharge within our cap banks, and basically we can get an improved dynamic performance, and we're going to be talking about that next week. How we can improve the dynamic performance of a STATCOM, increases its ratings because we're using a hybrid solution which consists of capacitor banks with fast discharge and STATCOMs, all built in to one piece of equipment. So it would be an AMSC STATCOM here, and here we're showing an 8 MVAR system, which would be 2 of their 4 MVAR DVAR systems, the coupling transformer, You would still cable over to it, but we would have the breaker and the disconnecting switch within our own gear, so which means that you have a single point of entry, as you see here. So a fully integrated solution. So that will be next week's Tech Talk. So I'm going to hold for a moment just to see if there's any questions. And it does not look like we have any questions. All right, what is a good filter type? Okay, so Talit asked, what is a good filter type to dampen natural harmonic resonance point at around the 40th harmonic? Here I would say that you would want to consider a C high pass filter. No, actually, I take that back. C high pass filters, 5th harmonic and down. Here would be a high pass filter. So standard high pass filter, tuned very high up. You would have to go with a pretty heavy damping factor up at that frequency to make a difference. So I would say you'd want to go with a relatively low damping factor. I want to make sure I get that right. Low damping factor to really flatten the curve and then tune around the 40th harmonic. It's very tricky when you have a high frequency resonance, because when you tune to the 40th harmonic, you get a resonance beneath the tuning point. And that resonance is going to move around based upon the short circuit impedance of the network. So putting a resistor around the reactor will help to flatten that resonance out, but that resistor value would have to be relatively low. Okay, low in value, which means low damping factor. So low resistance, low damping factor, and you'll get rid of that resonance. That would be my first attempt. But you have to make sure you do not magnify the other harmonics where you get the increased impedance because of resonance with that filter bank against the source impedance. So hi, if anything else, okay, so this is from Mansour. If everything else is on the system is with 200 kV BIL, then should we not stick with 200 kV BIL for the switches as well? So that's a good question. A lot of the other gear in the substation, okay, will be rated 200 kV BIL because it's exposed to the environment. But if it's metal closed solution, if you have roof bushings coming in, we would rate those roof bushings 200 kV BIL. But inside the gear, we would go with 150. And it's really about exposure. So very often outdoor gear is rated 200. Part of it's because of contamination of the bushings and potential for wildlife hitting the insulators. But once you get inside the gear, go with 150, and it leaves the choices open for us. So Ian, I see you are on. Hi, Ian. So hi, if everything else in the system is, all right. So again, 200 kV BIL, same question. So again, we would recommend you drop the BIL inside the gear. And just because you've chosen to go 200 kV BIL inside the substation where the bus bars might be exposed, once you get in the enclosure, go with 150. So if there's no more questions, we'll see you next week. It's going to be an interesting conversation with AMSC. They're going to present this concept of the hybrid STATCOM filter / capacitor bank system. So thank you. And don't forget to tell your friends to tune in to the Tech Talk. Great way to earn some PDH contact hours. Hit that like button down below so we can increase the number of people watching. It'd be great to have a higher participation. Thank you for coming on.